Let me take you back to 1975. It was the year Canada adopted the metric system. The CN Tower opened. On a stormy night in November, the Edmund Fitzgerald sank in Lake Superior. Saturday Night Live debuted, created by a Canadian producer. And the Toronto Maple Leafs were mired in an 8-year drought of not having won the Stanley Cup. And on October 8th of 1975, Canadians across the country heard this for the very first time.
Good evening, this is Quirks and Quarks. I'm David Suzuki. Welcome to my show, a weekly peek into the world of science and scientists.
Well, hi, I'm Bob McDonald, and welcome to my show. And the 50th anniversary of Quirks and Quarks. Yes. We're here at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. And it's unbelievable, but it's been 5 decades and roughly 2,000 programs. So we're celebrating. And we're celebrating here at the Perimeter Institute, where they are marking their own 25th anniversary. Now, we're going to talk about the last 50 years of science that we've covered on the show, but we're also going to rocket into the future and talk about a group of Canadian researchers from a wide range of disciplines about what the next 50 years might hold. So you're getting a full century of science. And I should put out that these people are putting a little bit on the line here because we might hold them to their predictions in our 2075 anniversary episode of the show. But first, we have a very special treat for you. In early 1975, Quirks and Quarks was just a dream, a twinkle in the eye of a CBC producer named Diana Filer. Now, Diana is still with us at the ripe old age of, as she says, 34 Celsius. I think that starts with a 9. 50 years later, she agreed to tell us the origin story of Canada's favorite radio program. I spoke to her at her home in Vancouver just a couple of weeks ago. Here's part of that conversation. I'm sure you've heard this before, but Diana, welcome to Quirks and Quarks.
Thank you so much.
So,
do you work there too?
I do, yeah. I enjoy it. It's a wonderful program.
Yeah.
So take me back to 1975. Where did the idea come from to do a science show on CBC Radio?
Yeah, science. You know, I had a show called Jerusi, and we would have science items in. And I said, let's have a whole show and not just items. Mm-hmm. No, said everybody. But was it Peter Zosky? It was Morningside. Mm-hmm. And Morningside, we had little items. And they said, we don't need a whole show. And I said, but the department is called Arts and Science. And you've got all these art shows. You've got music, drama, comedy.
I used to work on Morningside. I was one of the science contributors to Morningside, believe it or not.
But you were an item.
Yeah. Okay, so was it hard to convince management to do a science show?
It took 2 years, but at one point during that 2 years, I went to an old UBC reunion in Toronto, UBC. And David Suzuki was there too. So after we'd had chat and things, I asked him would he be interested in doing a science item for us on radio. And he, yeah. But then I gave him my card, and darned if he didn't answer it. Somehow I got money for a trip to Washington for the AAAS meeting. Do I have to say what it is?
American Association for the Advancement of Science.
Thank you. And while we were there, so was Isaac Asimov.
Famous science fiction writer.
Yes, that's right. And Suzuki got an interview with him, but the show hadn't even started, Quirks and Quarks. Margaret Lyons, the then head of department, one day I said, listen, Margaret, tonight listen to the show. The first hour is going to be a pilot for a science show. And she said, all right, I will. And she did. And the next morning I hear, she's very short and she had very high heels and she'd be coming down the floor. And you could tell by the gait what she was thinking. I said, oh, is that good? She said, that was a good show. Why don't we try and do something with it? I had two names, Quirks and Quarks. Or neither Margaret nor I could remember the other one afterwards.
But it stuck, and it's the best name in radio.
Oh, it's a good name, isn't it?
Quirks and Quarks is a great launch pad for all kinds of people. We've had scientists say that they were inspired to get into science because they listened to the show. Okay, so here we are half a century later. Have you been listening to the show? Have you been listening to the show?
Oh, yes, from time to time I listen to the show, but don't ask me what's my favorite.
Well, I want to know, how are we doing?
Oh, you're doing brilliantly.
And I am very, very pleased and honored to announce that Diana Filer is here with us tonight. Diana, stand up and say hello. Diana Filer, everyone. And we have another part of the Quirks and Quarks origin story in our audience today. Diana might have pioneered the show, but Ivan Fatsan was the extraordinarily youthful showrunner in its first year. And from that career highlights, he went on to less prestigious employment. Things like CBC's Vice President of English Television and the President and CEO of CTV's Globe Media. Yvonne, we're happy that you could make it with us tonight. Yvonne Fatsan. Well, we promised you 100 years of science, and it is time to deliver. One of the most significant concerns in the early 70s was population growth. Global population had hit, wait for it, 4 billion souls and rising. And it wasn't all that clear to many that we could continue to feed all those hungry mouths. One of the loudest voices articulating these concerns was Paul L. Ehrlich, the author of the massively influential 1968 book, The Population Bomb. Here he is from the February 18th, 1976 episode.
It is quite true that the worst population growth in the world from the point of view of our resources of the world's environment goes on in the overdeveloped countries because of the enormous impact we have on the environment and on the non-renewable resources. So you could say that Americans are busily wrecking the world, but on the other hand, the Indian overpopulation is busily wrecking India because there's just no hope of any kind of economic development when you've got to keep plowing whatever resources you can scrounge back into trying to feed and take care of unsuccessfully more and more people. Today, if the weather doesn't go bad on us this year or next, we would have enough if we divided it up evenly. But what about tomorrow, particularly when the population is going to double in something like 35 or 40 years? Clearly, you're coming close to absolute limits.
Well, here we are, 2025, and the population has doubled to more than 8 billion. And we continue to worry about how we can feed the world's teeming billions without exhausting our poor planet. Well, here to tell us about just how we've done that and what the next 50 years will look like is Dr. Evan Fraser, geographer, food scientist, and director of the Arrell Food Institute at the University of Guelph. Dr. Fraser, welcome back to Quirks and Quarks. Okay, so why didn't the population bomb explode as we doubled our numbers since 1975?
Yeah, make predictions, at your peril. Some context. 225 years ago, I'm even going back further in time, a very grumpy British clergyman named Thomas Malthus looked out at the rapidly filling British countryside and went, oh dear, we have a problem. And he said, food production is linked with land, so you only get a little bit more each year. Population growth is linked with the amount of babies we can produce. It goes really fast, and we're going to have a crisis. What every Malthusian since Thomas Malthus or Paul Ehrlich The mistake they made is to ignore the fact that we can innovate, that food production has stayed growing faster than population growth has. And there is more food on the planet per person than at any point in human history. There's 3,000 calories available for every man, woman, and child on the planet today.
So how did we do that?
Well, we did it through technology. We bred better seeds, we used irrigation, we used fertilizer, and we have increased the amount of food. But there's a caveat. There's a really important caveat. The fruits and vegetables that we all ought to be eating more of, we don't produce enough of. So we produce lots of calories, lots of grains, lots of fats. We don't produce enough fruits and vegetables.
And what have been the environmental costs to all of that development?
Well, this is the negative side of the story. That was the positive side. The negative side is a third of the world's greenhouse gas emissions come from food and farming systems. Wow. Agriculture and fisheries are our primary culprits in our losing fight to protect the planet's biodiversity. And agriculture is the biggest user and the biggest polluter of fresh water on the planet. So we have a lot of work. But agriculture could be a solution to every single one of those problems. And there's farmers around the world today who are part of the positive change that we all need as a planetary species.
Okay, so let's look ahead 50 years. What do we need to do from this point?
So I think to answer the 50-year forward question, we have to do a little bit more looking at where we've come from. We have focused on producing more food per acre in the last 50 years, and that has been a single-minded focus of big foundations, government programs, research corporations. If we broaden that focus to include sustainability and nutrition, climate mitigation, climate resilience, we can accomplish tremendous things. I was talking to a rancher recently who invested in 2 drones. One drone goes out and can identify invasive weeds within hours of them germinating. The next drone goes out and sprays them with a minute amount of herbicide. And as a consequence of those sort of technologies, we can produce a lot more healthy and nutritious food with a lot less environmental impact, and those innovations are just coming.
What about things like we hear about vertical farming, that kind of stuff, aquaculture?
So I'm a big believer in the idea of vertical farming. We've got the opportunity now to do what we call controlled environment agriculture, producing healthy, locally sourced produce with a relatively small carbon footprint, very small land footprint, almost no water, available at year-round, even in winter climates. Now, there's a lot of complexity in how to get those technologies used in those ways, but the technology is available to do that now.
Okay, but now what about reducing the amount of fossil fuels that are needed? Because I know they're involved in making fertilizers, for example.
Oh, that's such a good question. So fertilizer, for people's benefits, is largely made up of nitrogen. In order to create nitrogen that plants can use, it's an incredibly energy-intensive process. You have to heat air up, you have to squish it down to create plant-available nitrogen. There's a new generation of fertilizers coming onto the market where it essentially inoculates the plants with microorganisms to allow them to access their own nitrogen on demand for plants. Some plants, leguminous plants, do this already. Increasingly, scientists are developing technologies and tools to allow other crops to achieve that same sort of feat.
I've also seen an electric tractor, so that's coming.
Absolutely, absolutely.
Okay, so does this mean then that we're going to have to change our diet to farmed insects and vat-grown algae?
The short answer is no, not unless you want to. But having eaten some pretty good algae burgers and some not bad insects in my life, I'm not opposed to that.
Okay.
2 things there. Yes, consumers are going to have to adapt. And if we just imagine the Canadian nutritional guide, the Canada Food Guide, with a mostly plant-based diet with relatively small amounts of protein, that's the sort of diet that most of us in the affluent parts of the world are going to have to lean into. Mm-hmm. And there's a whole lot of really interesting innovations in the broad area of food science that are going to expand consumer choice while reducing environmental impact. Things like precision fermentation, where we, instead of producing alcohol at a fermentation, produce proteins or other food ingredients out of very fancy fermentation vats. That gives us a whole new set of opportunities, a golden age of food science that will increase consumer demand, not limit it. And there might be some algae and some insects. Who knows?
So if we want to eat more, we have to drink less.
I don't think it's a trade-off. I don't think it's a trade-off. At least not in my world. There's no trade-off here.
Okay. Now, you're painting a very optimistic picture here about the future. What kind of technologies are we going to need?
So I just mentioned something called precision fermentation, where instead of fermenting booze or other things, we ferment proteins. That is an amazing technology. 5 years ago, if we had this conversation, I would have said it was 30 years away. I can give you multiple companies working in Canada today that are doing precision fermentation. Vertical farming, another one that I think shows tremendous promise that will allow us to eat better.
What could sabotage our food production?
Well, I mean, the technologies we're talking about work in the real world. Consumers could reject these technologies. Climate change could happen faster than we can innovate and adapt. Politics could dismantle global trading agreements and leave entire populations out of lunch. These things can happen, and they mean that for those of us who are working on the great challenge of feeding the future, this is one of the big challenges of the generation.
But we do need to eat.
3 times a day, mostly.
Dr. Evan, thank you so much.
Thank you.
Dr. Evan Fraser. Dr. Fraser, thank you very much. Dr. Evan Fraser is director of the Arrol Food Institute and professor of geography at the University of Guelph. He's also co-chair of the Canadian Food Policy Advisory Council, a fellow of the Pierre Elliott Trudeau Foundation, and a fellow of the Royal Canadian Geographical Society. Now, one of the things that Quirks and Quarks has always promised our listeners is that we'll explore the mysteries of the universe. So, cosmology, the structure, origins, and evolution of space and time. It's a familiar topic dating back to the various early programs on this show. And in our first season, we welcome one of science's great communicators, the cosmologist Carl Sagan, to explain one of the universe's most fascinating phenomena in his own inimitable style. Here's Carl Sagan explaining the mystery of black holes.
The essential properties of black holes are that they're black and that they're holes.
Carl Sagan, everyone! Carl Sagan! Yay! Okay. That wasn't one of the shortest interviews in Quirks and Quarks history. Here's a little bit more from that interview.
Black means there's no light coming out of it. And the reason for that is that the gravity is so high, the local acceleration due to gravity, that even light cannot get out. Even photons, faster than which nothing can travel, do not have escape velocities. So it can be plenty bright down here in this black hole, but from the outside, it's completely dark. Nothing gets out. However, gravity gets out. And so if you're not paying attention and you blunder into the vicinity of a black hole, game's all over. You get sucked right in.
So we understood the basics of a black hole back in 1975, but in many ways since then, we didn't know how much we didn't know about the universe. And 5 decades later, we still don't know a lot about the universe, but we have a much more precise understanding about how much we don't know. We even have a number for it, 95%. And to help us unpack all this, let me introduce Katie Mack, the Hawking Chair in Cosmology and Science Communication, right here on her home turf at the Perimeter Institute for Theoretical Physics. Hi, Dr. Mack.
Hello.
So how have we come to this precise understanding that we don't know 95% of the universe?
Well, the problem is that we have discovered a lot about what the universe is made of in terms of how it affects the things that we can see. So we've discovered that there is something called dark matter, which is some invisible stuff that seems to be holding the galaxy together. It seems to be sort of the foundation upon which all of the matter we see is built. It's about 85% of the matter in the universe. And we know that because of how it affects the things that we see, stars and galaxies, how they move around, how light bends in the presence of strong gravitational fields. But it is invisible as far as we can tell. And that means it's very hard to figure out what exactly it's made of. We know how much there is, we can survey it, we can map it out, but we don't know what it's fundamentally made of because it's just very hard to see, it's very hard to detect. Okay. Then the other problem is that in the 90s, we discovered that the universe is expanding faster than we expected, and speeding up in its expansion. And that is due to apparently something we call dark energy, which is some kind of invisible stuff that seems to be making the universe expand faster. But we can't see that either.
Okay, so dark energy and dark matter make up 95% of the universe.
Yes.
And I know when a scientist says dark, that means, I don't know.
It means that we are in the dark, but it also means that it just isn't making any light.
Okay, so how are we going to untangle the mystery of dark energy and dark matter?
Well, there are a few things that we can do to learn about both of these. So for dark matter, we can look for it in terms of how it affects the motions and properties of things out in the universe, how it affects the shapes of galaxies, the formation of galaxies, things like that. We can also look for the possibility that dark matter might occasionally interact with regular matter through something other than gravity, which would be fantastic, because then we could actually learn something about what it's made of. So we can look for weird amounts of radiation coming from places like the center of the galaxy, or sort of strange high-energy particles emitted from other galaxies. Then we can also do experiments in the lab. We can build big underground detectors and hope that dark matter will come through and bang into something in the detector. And we can do experiments with particle colliders, where we smash particles together and hope that something that comes out is able to escape the detectors, and maybe that was the dark matter that we just...
And some of those detectors are here in Canada, in Sudbury.
Yeah, the Snow Lab, yeah, exactly.
Okay, so far, where's all this leading?
Well, hopefully it's going to lead us to a better understanding of the universe. So if we understand what dark matter is, then we know what most of the matter in the universe is. If we know what dark energy is, we know what most of the sort of stuff, the energy density of the universe is. But more importantly for me, I think, is that if we understand both of these things, then we understand the fundamental physics of the universe better, because neither dark matter nor dark energy are included in our standard model of particle physics. They're not part of the sort of theory of all of the particles we've ever detected. So if we can figure out what they are, that leads us to the next theory and a better understanding of fundamentally how physics works, and who knows where that could lead.
Okay, so we're mapping it out. We know it's there. But are we getting any closer to understanding what it is, or what they are?
Well, I think so. We're getting clues in various ways from observations, from experiments. With dark energy, we're learning about it with galaxy surveys. We're getting weird hints of possible anomalies with galaxy surveys. The problem is that unlike something like the Higgs boson or even gravitational waves, there's not a sort of place where we're pretty sure we're going to find it at a particular spot. Like with the Higgs boson, that was discovered in 2012 at the Large Hadron Collider, we were pretty sure it was going to be there. Or at least we had sort of a range of energies where if we didn't find it there, then we'd have to rewrite everything, but we're pretty sure where it was going to be. Okay. And with dark matter, dark energy, we don't really have that. There are a lot of possibilities. We're exploring all of them, but we don't know when we will either find it or find something completely different. Okay,
so can you say then that 50 years from now, we'll know what dark energy and dark matter are?
I can't say that for certain, but I'm very, very optimistic. I think that we are getting so many clues. We are being so creative about how we look for these things. I really think that we're going to find something amazing.
Dark.
Yes.
Dr. Mack, thank you so much for your time.
Thank you.
Katie Mack is the Hawking Chair in Cosmology and Science Communication here at the Perimeter Institute for Theoretical Physics. Now, the first season of Quirks and Quarks was in the dawn of the personal computing era. In 1976, in fact, was when the Apple I computer first appeared. Of course, in industry and government, larger computers were already ubiquitous. Here's David Suzuki introducing a segment from early in 1976 that should resonate with us today.
Could we have predicted how incredibly useful computers would be, how dependent on them we'd become, and how rapidly computers would evolve? Now there are very sophisticated computers whose central brains are as small as the head of a match, and they're cheap enough for most people to buy one. Last week, in the first of two reports on computers, we discussed crimes committed with computers. Tonight, Richard Rosenberg of the University of British Columbia discusses his field of specialty, which is artificial intelligence. First, exactly what is artificial intelligence?
Okay, well, I guess a simple definition would be something like trying to program computers so that they exhibit behavior which, if humans did it, you'd call it intelligent.
Well, artificial intelligence was certainly not the buzzword back then that it is today. And to help us understand the last 50 and hopefully the next 50 years of computer technology and AI, I'm joined now by Dr. Luke Stark from the Faculty of Information and Media Studies at Western University in London, Ontario. Dr. Stark, welcome to our celebration show.
Thank you for being here. It's great to be here.
So obviously, AI was much closer to a concept than a reality back in the 70s. What got us to where we are here today?
You know, I think AI has always been closer to a concept than a particular technology, right? The idea of creating artificial life, it goes back actually 5,000 years, not just 50 years. And there have been various different imagined ways you're going to get to that goal of an AI, a sentient machine or a living machine. In the 80s, you know, it was one set of computer tools. Then, you know, in the 90s, actually, and 2000s, a totally different set came in, machine learning. Maybe you've heard this word, machine learning. The idea that computers can take a whole bunch of data, a whole bunch of information, and look for patterns in that data. And then they learn those patterns, and they can apply that learning to other sets of data. So really, fundamentally, that's what today's AI is based on. It's this machine learning. These are, you know, sophisticated pattern matching computers.
But now it's hard to tell. When you ask a question and you get a voice coming back, it's hard to tell that's a machine.
It's true, right? And there's been a lot of work by AI companies, especially these days, to make these systems seem human, appear human, you know, be like a human. You know, when people think of AI, they think of ChatGPT these days. That's the thing right into their mind, right? Well, ChatGPT is based on what's called a large language model. It's a big database of words, parts of words, and through a lot of very powerful computing power, you can kind of put together, you know, the relationships between those words. What word is most likely to come next and after? And there's a lot of other stuff that goes in there too, but the key point is that these systems are really being designed by companies like OpenAI that develops ChatGPT to mimic humans, right? You know, that like first person, you know, oh, I'm just a chatbot. That thing, that's a design feature. The actual LLM doesn't do that. So it's hard to tell, and I think, you know, there are some business reasons why that's the case, right? I think these companies would really like us to think that these tools are sentient. They pick up on something that's called the ELIZA effect, which is this you know, an effect that was named after a chatbot actually back from the 70s, called ELIZA. No fancy machine learning, nothing like that. But it was really enthralling. People would play with it, and they would think they were having these kind of, you know, in-depth conversations with it. So the ELIZA effect is when people project sentience, complexity, you know, emotions onto a chatbot. Right. These days, a lot of people are enthralled with the ELIZA effect.
Right. Of course, Hollywood's always had fun with that with AI. It's usually something evil. And interestingly, Rosenberg from UBC, who we heard from in that clip from 1976, he was a pioneer in thinking about the ethics of AI. So how well has research into the ethics of AI come along?
You know, I think one of the interesting things about the history of AI is that there's actually a really long story about the research into ethics, social impacts, which is what I do. The guy who invented ELIZA, Joseph Weizenbaum, who I mentioned, he was so kind of taken aback by how much people were taken in by this very simple program that he wrote a whole book in the 70s about things, you know, what computers can do and can't do related to humans. And every decade or so, there's a big upsurge in that work. What seems to happen, though, is that when a new technical innovation, a new thing, maybe it's the personal computer, maybe it's the internet, maybe it's social media, maybe it's smartphones, maybe it's the first wave of AI about 10 years ago, maybe now it's LLMs. When those come in, you know, for whatever reason, you know, politicians and the media, you know, they tend to forget there's been all this other research on the impacts of these tools. And all of a sudden, everything is shiny and new and amazing and great. And so you have to kind of rediscover that research over and over again. So it's there, but you know, and you know, people have been thinking about these problems for a long time, but we don't always realize that when we hear it in the media.
Okay, so where's it going from here?
Yeah, I mean, I think, you know, AI tools are, very in vogue right now. Everybody knows this. A lot of people listening might be having intimate conversations with ChatGPT, and I think the more these tools get put into various facets of our lives, into our smart appliances, our fridges, certainly in our phones, we're going to see more and more people interacting with these systems like they're social, right? I think that's dangerous for a couple of reasons. One of which is that actually you're giving an awful lot of personal information to these chatbots, right? You're having this conversation, it feels like it's with a person, but it's collecting a lot of information. More generally, so people talk a lot about AI sentience, about artificial general intelligence or AGI. I'm gonna put my prediction out here. I don't think we're gonna see artificial general intelligence in the next 50 years. I don't think so. I think that the conceptual challenges to that are so big that unless something really, really major happens in computing, the fundamentals of computing, we're not going to see that.
Wow.
So if I'm wrong, you can send David Suzuki can come and make me eat my hat.
You don't even think quantum computing's going to make it?
I think quantum computing, would be interesting. The thing about quantum computing is that right now it's so detached from the applications that it's not clear how it's going to affect it.
Wow.
But my big prediction, for the social impact of these systems is that there are going to be a lot of disagreements and a lot of fights about who gets to develop them, who gets to control them, and who gets to regulate them, who gets to decide what role these powerful computational tools, these powerful statistical tools with little human voices, how much power they have in our society.
Okay, so you don't think it's going to come to the point 50 years from now when my AI avatar is talking to your AI avatar, wondering about what happened to biological intelligence and how we can bring humans back to thinking?
I think it's more likely that you and I will be having this conversation.
Let's hope so.
Yeah.
Dr. Stark, thank you very much.
Thanks so much.
Luke Stark is an assistant professor in the Faculty of Information and Media Studies at Western University in London, Ontario. He's also a Canadian Institute for Advanced Research, ASRI LE Global Scholar with the Future Flourishing Program. I'm Bob McDonald, and this is a special edition of Quirks and Quarks. We're celebrating our 50th anniversary in front of a live audience at the Perimeter Institute for Theoretical Physics, and we're discussing the last 50 and the next 50 years of science. Now, Quirks and Quarks didn't shy away from contentious science in its early years. Here's one example of how we were on the cutting edge in our fourth program in 1975.
There's a lot of controversy right now over whether we're in for another ice age or whether the Earth is heating up. It would be very helpful if we had accurate records of the weather for the past 1,000 years or so that we might see if there are any obvious cycles or trends. Scientists in New Zealand have found a way to infer very accurate temperatures up to 9,000 years ago. The technique involves a measurement of deuterium, which is a form of hydrogen with an extra neutron. I think Asimov is going to tell us about deuterium in one of our later shows. The secret is the ratio of deuterium to hydrogen found in tree rings.
Climate change. Have you heard of that? Arguably, it is the scientific issue of our age, with enormous implications for the future of our planet and our species. Dr. Laura Tozer is studying what's necessary for the climate transition we're going to have to make in the next 50 years, if not sooner. She's from the Department of Physical and Environmental Sciences at the University of Toronto, Scarborough. Dr. Tozer, welcome to our program.
Thank you so much.
So David was talking about the climate debate in the 1970s. Some were saying we're in for another ice age. Others were saying it's going to get warmer. What's happened in the intervening 50 years?
Yeah, it's really been a masterclass in physical science. A way that we have settled and we have known for so long that humans have caused climate change. And it's really amazing the scientific work that went into this. You know, the example from the quote, but there was the same kind of signal being found in all sorts of records all around the world, all by independent scientists, who then came together in international spaces to collect that work together, to call for action for decades. Unfortunately, it's also been a masterclass in what social scientists call fossil fuel obstruction or carbon lock-in, where basically fossil fuel interests have been lying to us for pretty much all of those decades as well, trying to make it appear as though there's uncertainty.
Well, pessimism is pretty easy, especially when you consider that we've missed all of our climate goals, and climate denialism, as you say, is part of the many, including certain administrations at the moment. So where do you think we'll go from here?
It's really easy for people to picture apocalypse when we talk about this topic. And so I really want to talk about a future looking ahead 50 years where we've succeeded, where we've done what we need to do in order to address climate change and really tried to find all the ways that we can make that reach everyone. I did some work with some young people last year, and the mental health burden of trying to kind of grapple with the climate crisis is really serious. Yeah. And so I think we need to do more work imagining what flourishing looks like over 50 years. And the transition away from fossil fuels in our energy system will be a fundamental part of that.
So what kind of technologies will we need to do that?
You know, the nice thing about it is that we have a lot of the technologies that we need already. You know, it's one of those things where we have all sorts of renewable energy solutions, we have all sorts of components of it, but a lot of them need more innovation to become cheaper, easier, smaller, more accessible. Things like balcony solar panels that you can, move when you move apartments. That's the kind of innovation that will make these energy technologies available for everyone. But I think there's still going to be a lot of development in a few different areas that'll help us make this transition to fossil-free energy, and that'll be things like batteries. You know, the way that batteries have developed over the last few years has really been astounding, and so I think that will continue because it's a really important part of our energy system. And this will be about improving their performance, but there are a lot of people that are also working on innovating with how batteries work fundamentally so that we can remove some of that dependence on critical minerals linked to social and environmental injustices.
I've already met several people who put solar panels on their roof, they drive an electric car, and they charge the car from the house, and they drive for free.
Right?
That's
right?
a nice feature to think about, isn't it?
Yeah.
So what kind of transition do we need to go through to get there?
We're looking at a transition that has a few key parts. One of the fundamental parts of it, though, is what we call electrification. And so this is the way that we move a lot of the things that we do in our life away from fossil fuels and onto electricity instead. And so this is another area where I think there will be a lot of innovation over the next 50 years, all the different components that go into this electrification transition. And so it's things like modernizing our electricity grid so that they can be 100% renewable energy and we can take advantage of that free fuel. You know, it's the wind, it's the sun, it's always there.
Energy is really supporting our lifestyle here, so are we going to have to make sacrifices to make the transition?
Short answer, no.
Oh.
What we're looking at here is a fossil energy system that's actually really inefficient. It wastes a ton of energy to live in this fossil-dependent system that we do. And the sustainable energy system is one that will be much more efficient just because of the technologies that we use. They're much more efficient than some of the fossil fuel combustion, for example. But it's combined with that efficiency and renewable energy that has that free fuel. So you're looking at an energy system that's actually based on abundance rather than scarcity. But the other part of it is that we choose the way that we design our energy system and what it does for us. So we can decide we want it to give us hot showers and cold beers. It's Amory Lovin's quote from the 70s, still true today. You know, people don't care how it got hot or how it got cold. And so why don't we do that in a way that doesn't cook our planet?
Okay, so paint me a picture 50 years from now. What's it going to be like?
Well, I think it'll look different all over the country. So we'll have stories of northern energy sovereignty, we'll have stories of, kind of the urban community. But for example, in a rural community, this might look like that 100-year-old farmhouse that the drafty one, right, with the fuel truck arriving for that really hard to pay bill. Instead, that home will be efficient, it'll be comfortable, people will be healthy in it. It'll have a heat pump instead, solar panels on the roof. That farm will have new income coming from the renewable energy that they've built on their land. And that exists already. We just need it to be rolled out across the country. And the other thing that we can see is, if we look at a more suburban community, maybe, then you're looking at maybe a new apartment building built with modern technology. You've got the 3 generations living in this 4 bedrooms, but they're right next to the commuter rail, right? So all 3 of them can go 30 minutes to where they need to work. You've got this building that's resilient to the impacts of climate change. It's got the solar panels integrated. Maybe it's on the front of the building, not even on the roof, because they're inventing these technologies that can be built right into the sides of the building. But it's a place where I think the important thing to think about as we think about flourishing 50 years ahead is that much like now, energy is kind of in the background because it's fundamental. We really only notice our energy systems when they're failing us somehow, when they're broken. And so there'll be this support system for flourishing as we think about what kind of a sustainable community looks like in the future.
And energy will come from many different places, including your own home.
That's right.
Dr. Tozer, thank you so much for your time.
Thank you.
Dr. Laura Tozer is an assistant professor of environmental studies at the University of Toronto and director of the Climate Policy and Action Lab at the Department of Physical and Environmental Sciences at the University of Toronto, Scarborough. Well, one of the features of the first season of Quirks and Quarks was a very special weekly guest, the legendary scientist and science fiction writer Isaac Asimov, recruited by producer Ivan Fetzan. Now, for the first time, he came on each week to explain and unpack the science behind a particular word. So here's an example from one of his appearances in May of 1976.
Let's go straight to our New York expert on science words, the internationally renowned science fiction writer and popularizer of science, Isaac Asimov. What's the word tonight, Isaac?
How about transistor? There's something
That's a
that
good one.
we're all familiar with. Now, it was in 1948 that an English-American physicist and 2 co-workers first worked out this little solid equivalent of the radio tube. It transferred electrons across a material that resisted it. You had a transfer across a resistor and a transistor. These days you can make them so tiny that you can take a small chip of silicon and put thousands and thousands of different electrical devices on it.
Now, one of the electrical devices that we all have in our pockets, but not here in a theater, of course, is our cell phones. So how many transistors do you think is in a common smartphone? Anybody have a guess? Shout it out. What do you think? 1,200, 12 million? Yeah. 20 million? Yeah. It's about 10 billion or so. 10 billion. And that's just in a cell phone. So when it comes to computer technology and things like automation and robots, we've come quite a way in 50 years. Well, to help us understand how far and where we're going, I'm joined by Dr. Ana Luisa Trejos. She's a professor in the Department of Electrical and Computer Engineering and the School of Biomedical Engineering and Canada Research Chair in Wearable Mechatronics at Western University in London, Ontario. Hi, Dr. Trejos. Welcome to our show.
Thank you so much.
Okay, so a smartphone is just one example of how far technology has come, but I want to talk to you about your field of technology that operates in the world more physically. So how far has automation and robotics come in the last 50 years?
Yes, so 50 years ago, robots already existed, but they were very basic and simple because their control systems were very primitive. With the invention of the transistor and the advances in integrated circuit technology, we have come so far in the miniaturization of microcontrollers that allow the robots to be intelligent, the sensors that allow the robots to perceive the environment, to the point that now we have robots pretty much everywhere, right? So when we think about the most advanced robots right now, a lot of us will think of an airplane that pretty much flies itself, or self-driving cars, but we don't necessarily have to go that far. We can think of assembly plants where robots are pretty much doing everything from moving parts to assembling parts to painting, quality control, and they're doing all of this in a very automated way.
Well, we also have these amazing videos of robots dancing, doing backflips, and robotic dogs running through forests and all of that. So what can we expect from robots in the future?
Yeah, so I'm going to start by thinking about how things have changed. So in the last 50 years, machines were very much one size fits all. So you have one machine and everybody has to deal with what that machine can do. I think the future, our machines are going to be a lot more customized, are tailored, not just to the person, but to the task that they have to do. So, for example, in my field of wearable exoskeleton, I think the idea of the bionic person is very real, right? So there's been a lot of advances in prosthetics where there will be an implant that is put on the brain of the person, and that will detect what the person wants to do, and it allows them to feel like the prosthetic is part of their body. So that's going to continue, but I think there has to be a little bit of a revolution in the way that we power these devices. So my theory is that we're going to get to the point where we can use our own energy, so human energy, to power these prosthetics, and not necessarily just for limbs, but any part of our body that needs to be replaced could be replaced by a robotic system that is worn on the body.
Wow. So how far will that go? Will we have like data from Star Trek? It'd be totally synthetic? I mean, how far can we go?
I think potentially if the person would need it, yes. But in most of our cases that we perhaps have all our parts, we would just wear something that feels like clothing, and it has all of the sensors and the actuators around it, and it allows us to move better or perform whatever action we can't perform by ourselves. And then it could even enhance our performance, so go beyond our natural abilities and create sort of like a superhuman that allows us to perform way beyond.
So will I ever get my robot butler?
I think that's a very real possibility. Robot butlers are, the way that I envision them, I think they're going to be more for the disabled or the elderly who not just need help with their day-to-day tasks, but also need that social companionship. I think for the majority of us that we want help with our chores, the boring stuff, I think it's going to be more like intelligent buildings, intelligent homes that do all those chores for us. So we can imagine a self-cleaning toilet or a bathroom that cleans itself, or chutes around the house where you just throw your laundry and somehow it gets through the house, laundered, folded, and back into your wardrobe.
I like that a lot. You know, you're reminding me with these powered prosthetics of a program I watched back in 1975, The $6 Million Man.
Yes, exactly.
He had a bionic eye, one arm, and two legs. $6 million back then was, what is this, $36 million today.
Yes.
Can we bring that price down a little and make this stuff accessible for everyone?
Yes, absolutely. So some of the work that we're doing is trying to come up with more traditional manufacturing techniques to create these devices. For example, simple things like sewing and embroidery, where we can create sensors and actuators that are made from conductive thread, again, going back to our clothing, but that don't cost that much more than a regular outfit.
Wow, good news. Dr. Trejost, thank you so much for your time.
Thank you so much.
Dr. Ana Luisa Trejost is a professor in the Department of Electrical and Computer Engineering and the School of Biomedical Engineering and Canada Research Chair in Wearable Mechatronics at Western University in London, Ontario. Well, David Suzuki, the first host of Quirks and Quarks, trained as a geneticist, and he brought that experience to bear on the program. But in the last 50 years, perhaps no area of science has been transformed more than his field, the science of the blueprint of life. Here's David in March of 1976 with an efficient summary of genetic science at that time.
Humans probably have between 1 and 2 million genes. Fruit flies have about 100,000, and bacteria 500 to 1,000. There are exciting new techniques for cutting up strings of genes and sticking the pieces into bacteria. and all 100,000 genes of fruit flies have now been inserted in little pieces into bacteria, and there the pieces replicate perfectly well. That turns out to be extremely interesting because it's possible now to study what turns these genes on and off. And eventually, scientists talk about being able to isolate genes from humans, sticking them into bacteria, and getting the bacteria to make things like hormones, insulin, or blood clotting factors for hemophiliacs. The technology for all of this is first being worked out with fly genes.
That the best informed minds in genetics in the 70s had just a few things wrong. 5 decades of work later, we now know humans have only between 20 and 25,000 genes, not 2 million. And there's a little less difference than we might have thought between us and fruit flies, who have something like 15,000 genes. We vastly increased our knowledge of how genetics shapes us and contributes to our health. But if our next guest is right, we're in line for another kind of genetics revolution. Dr. Yvonne Bombard is professor at the University of Toronto. She's also a scientist and Canada Research Chair at St. Michael's Hospital, Unity Health Toronto, where she directs the Genomics Health Services Research Program. Dr. Bombard, welcome to our program. So what have been the major leaps forward in genetics in the last 50 years?
The leaps have been bountiful, luckily, and we've seen genetics and genomics science really penetrate public health and day-to-day healthcare of all Canadians. For example, did you know that every baby that is born in a hospital in most of the industrialized world is actually getting their very first genetic test? The little heel prick test that takes a little sample of blood from the babies to do the very first genetic screen on all of the babies that are born.
Wow.
And that's been happening, and that's one of the premier examples of public health reach of where genetics has come. We've also seen the technologies like sequencing, where we're reading people's genetic codes or their genomes, also advance in leaps and bounds. For example, did you know that it took hundreds of millions of dollars and years to sequence or map or read one genetic code? And now we're doing it for a couple hours, for a couple hundred, all the time.
I remember the Human Genome Project, and it took years. It was an international effort just to identify all the genes in the human DNA. They were comparing it to going to the moon in terms of how much effort it took. Now they're doing it when a baby's born.
Absolutely breathtaking, yes. And we're doing it every day for patients in hospitals.
Okay, so that's identifying the genes. How has this been turned into human health and medicine?
Yeah, so our focus for the last 50 years not only has been to map and bring down the costs and the precision of the sequencing technologies, but it's also to understand how these genetic changes are associated with human health and conditions and other human diseases. And since that time, our focus now, today, has been bringing that knowledge to the bedside table, from the bench to the bedside table every day for cancer patients writ large, for heart disease patients writ large. So there isn't an area or a specialty of medicine that hasn't used genetic testing or genetic information now to tailor patients' management.
So how might this applied genetics evolve in the future?
So right now, genetics is a quasi-boutique specialty where it is quite limited now to hospitals that are in urban centers, academic centers, tertiary hospitals, and you would be hard-pressed to find a doctor or a practicing community health provider that has the confidence and uses that technology or the test results in their practice for their patients every day. But that's changing. And with work that we do, as well as all of us that are on the front lines trying to find the best ways to bring effective technologies in an ethical way to the bedside, we'll be in a very different place. We won't be in a place where patients are sent off for genetic testing and waiting for weeks to months and then having to schedule an appointment and figure out with a genetic expert what to do with those results. It will become part of mainstream routine care, where doctors will be using the genetic test results that have already been generated for every single person to actually dose the medications tailored to the patient. They'll be using your genetic test information to give you very specific lifestyle modifications to actually prevent and treat disorders earlier than what we are doing now.
So can you give me an example of how genetic work might help in diseases like cancer?
Well, we're already using genetic testing quite routinely. We sequence cancer patients' tumors, and increasingly we're sequencing their blood to find out, do they have cancer running in their family? Because if we know if the cancer patient sitting in front of us not only has cancer, which is a terrible predicament, but if we can actually identify what type of cancer, we can actually identify tailored medications that for some individuals, they will respond much better, have better outcomes, better survival, if we can actually genetically test them.
So how powerful of a tool do you think this will be in the future in terms of human health?
It's already a powerful tool. The issue is getting into routine mainstream healthcare. I mean, we already have gene editing, which is a breathtaking technology like my fellow scientists in the past. These are technologies that have been innovated anew today, providing new opportunities for treating disorders where we never had hope for treatment, like Huntington's disease or other blood disorders like hemophilia and sickle cell anemia, which can actually be treated at the point of care in individuals.
Wow. Well, it seems that we have a theme running through our show here about trying to bring the cost of these new technologies down. Can we do that with genetics as well, or is it going to remain in the realm of the wealthy?
Yeah, I think the costs are dramatically reduced now. What is it? If you build it, they will come. We are at the place where we need people to come. Unfortunately, because of the way technology has been introduced in society, only a sliver of the general public has participated in genetics. And just to provide behind the veil here, when we study a person's genetic code, what we're doing is comparing it to a reference. The problem right now is the reference sets that we have to compare are mostly made up of individuals of European ancestry. Therefore, our genetic science and our tests can't be as accurate for non-European ancestral groups. And so in the future, other than the cost, we need to have full participation of society so that full societies can benefit from the realization of genomic medicine.
So it becomes a global effort.
It's absolutely a global effort and very much a focus of our field.
Dr. Bombard, thank you so much for your time.
My pleasure.
Dr. Yvonne Bombard is a professor at the University of Toronto. She's also a scientist and Canada Research Chair at St. Michael's Hospital, Unity Health Toronto, where she directs the Genomics Health Services Research Program. Well, now it's time for some questions from you, the audience, here at the Perimeter Institute for Theoretical Physics. I'd like to welcome all of our panel guests to the stage. And producer Rosie Fernandez over here will find you in the audience for questions. And just a request, we've got limited time here from our panel, so if you're planning to have a comment more than a question, we'll save that for another time. So just questions, okay? So let's bring our panel up here on stage. And who would like to ask this panel a question on any of their related topics? Well, we pretty well silenced the room here. You don't have a question? Go ahead. Don't be shy. Okay, we have a young person here.
I'm planning to do a school project on how AI can take jobs, and I've been wondering about which jobs they can take. Like, obvious jobs like artists can't be taken, but I've been seeing how they're able to draw art by using human knowledge, and they're able to do physical stuff. So what jobs do you think would be inside actual danger?
So that's a great question. I think the thing about today's AI systems and jobs is that, so one of the big challenges with AI is that it, generally speaking, does not as good a job as a human in most cases, but it does an okay job in a lot of cases. And so I think the issue is going to be, is an AI system going to be thrown into a situation and into a job, right? And then there's still going to be a human involved, but that human's job is going to be more precarious and potentially less interesting, less creative, less fun. So you talk about art. So in fact, actually right now already, people who do art for magazines or for websites, they're already finding that their jobs are being replaced by generative AI systems. Except that sometimes the company says, oh, actually, this AI isn't doing a very good job. We'd like to hire you back, but we're going to hire you back for half the pay, right? So I think this is one of these situations where having a strong workplace, having a union, right, having labor rights is going to be really important in the future. We saw this with actors. I don't know, in the United States, actors and writers for TV shows and movies, they negotiated a contract last year that puts limits on what studios can ask them to do with AI. So I think a lot of jobs involving writing or creating things may well be at risk, and so it's we have to kind of get together and make sure that we push back on that.
Thanks. Okay. Thank you very much for that question. Okay. So we've had a little change of format here. Rather than Rosie running around, you'll have to come to this microphone if you want to ask a question. And you do have to use the mic so that the people at home can hear us. Sorry about that. Yes, sir.
Your guest who spoke about feeding an ever-growing population didn't mention that we all predictions are now that by the end of the century, population will level off and then start to decline. I'm just wondering how he thinks that might affect his field and how the rest of your guests think a falling population, which we've never experienced before, might affect their specialties.
Okay, so how might a falling population affect us? Go ahead.
So I'm very grateful that you asked that question, and you're right. The projections for how much population was going to rise over this 21st century have plateaued, and in many countries, such as Japan being the most notable, populations are coming down. This is good news, I think, for an environmental perspective. I mean, it's terribly challenging to manage from a social perspective, but for example, the combination of increased technology for agriculture and leveling population means that we have actually hit a point of peak farmland. And the most farmland that we farmed as a human species peaked about 20 years ago, and we've actually been rewilding land ever since. And so I can imagine a future where technology allows us to produce food very much more intensively on smaller plots of land, population is coming down, and we can then free up major parts of the earth for biodiversity reserves. That's the utopic vision, which I'm going to leave you on.
Okay. I'm just curious. I'm just curious, Dr. Tozer, do you have anything to add to that?
Sure, I'll add that because we have delayed climate action and energy transition for so long, we are in a real crunch time in the next couple of decades. And so thinking about less pressure from having to accommodate a growing population will be helpful in doing the energy transition as fast as we need to.
I want to ask a question about that. You talk about growth, not just population, but our economy is based on growth. Our economy is based on growth. So, and very often that's what dominates. I mean, how far can that go? Don't know.
I'll speak to that. First, I think one of the important things that we think about when we think about addressing climate change is thinking about reorganizing our society and our economy. And so I'm not an economist, but I know there's fantastic work being done on degrowth, on donut economics, on thinking about how we run the money part of our society in different ways that is a better fit for this climate change world.
Mm-hmm. Next question, please.
I'm fortunate enough that I make my living as a commercial beekeeper. And Dr. Fraser, you talked about that we're not producing enough fruits and vegetables and that. I know myself, I don't want to expose my bees. Like, I limit what I do because often there's so much pesticide and so much chemical involved in the production of these that my bees come out of there in worse shape than when they went in. What do you think the limiting factors are in producing those fruits, vegetables that we need?
So great question. And the collapse of wild and domesticated pollinators is one of the great, scary, apocalyptic stories of our generation. No question at all. So thank you for being a commercial beekeeper, and thank you for keeping the bees out there pollinating our food. Thank you. In answer to your question, we, much like you were referring to with this profligate fossil fuel system that we've got, we have a profligate pesticide system. But where we over-apply pesticides. I remember being a kid on my grandfather's farm in Niagara, just sort of spraying things willy-nilly in the 90s. Farmers today, enabled with the right technologies, like I mentioned earlier, don't have to do that. They can use minute amounts of pesticides, different methods entirely that don't involve pesticides at all to control let's say insects that you don't want. I think there is a very real chance that we will bring, agrochemical use down 50 to 80% in many agricultural systems, and that will reduce the pressure on pollinators.
I don't see that happening. I see integration with chemical companies and seed companies and more use of pesticides. My honey season ends now when they start spraying corn with fungicides because it kills a bunch of bees, and then I have to wait for that population to come back.
Yeah, we can talk about this outside. Yeah. I deeply share your concern. I think there are alternative pathways, though, but we're not necessarily on them.
Thank you
very much.
Hi, this question is for Dr. Mack. You had written a book called The End of Everything, meaning the universe. Mm-hmm. And so, based on your conversation today, how would certain discoveries or any discovery about dark matter or dark energy affect the predictions or the theories that you had about how the universe may end?
Yeah, thanks very much for that question. The biggest thing that would tell us something about the end of the universe is if we understood what dark energy is doing. So dark energy is the thing that's really dominating the evolution of the cosmos. It's making the universe expand faster, and we don't know how it's going to behave in the future. If it's what we call a cosmological constant, then we can kind of predict how things will go. You get to a heat death of the universe, everything kind of just fades away. But there are other possibilities for dark energy, and recently there's been some really interesting results from a survey called DESI, a Dark Energy Spectroscopic Instrument. It's a galaxy survey, and they've seen hints of the possibility that dark energy is changing over time in a way that we didn't expect. And if that's true, if dark energy is something that changes over time, it's not just a constant of nature, then the dark energy could do other things. It could make the universe expand in completely different ways. It could make the universe stop expanding and recollapse potentially in some point. And so if we really understood what dark energy was doing, how it works, then we would have a much better idea of what the long-term future of the universe would look like. Then on the other hand, if we understood dark matter, we would have a better understanding of how particle physics works, how the fundamental physics of the universe works, and that might give us hints about some other weird possibilities for the end of the universe, like vacuum decay, which is this possibility that the sort of Higgs field, this quantum field throughout all of space, might go through a change and change the nature of particles in the universe. So there are things like that we could learn a lot about those things by better understanding dark matter and dark energy, and by better understanding sort of the beginning of the universe, and that could give us hints about how our universe started, and then potentially like what are the big fundamental physics properties that it has, and how could that go into the future. So there's a lot that we're learning that hopefully we will start to be able to better answer some of those questions about the very, very far future.
Hello. I admit I've had a lot of bad luck with computers, and looking around the room, I don't think I'm the only one. So I think it's great that we have these technologies that are advancing like at an incredible rate, but relies on software that constantly fails and disappoints. And so while it's awesome that we can fit 10 billion transistors into a phone that I spend most of my day staring at, sometimes it doesn't recognize my own face. I'm just wondering, how is the software portion of this new exoskeleton being developed so that it only helps me improve my golf swing rather than try to strangle me instead?
That's a very good question. So a lot of the answer of that is in artificial intelligence. But I think you need to sort of sit down for a minute and think about what technology can do now. It is incredible that it can recognize your face and only your face to open up the phone, right? Like the amount of technology that has gone into that and the intelligence of the software itself to be able to do that is huge, right? So the fact that it doesn't work some of the time, it's better than human error in a way, right? So, but we do definitely have to advance more in the intelligence of the devices, especially when we're talking about something that is going to be worn on the body all the time, right? So that's why it's 50 years. It's in the future, along the 50 years, right? Like that ability to interpret biosignals, to interpret the motion of the person in order to identify not just what the person is doing, what they're trying to do, and then provide the support that they need. There is definitely significant work that is required. And there's going to be a lot of failures along the way and a lot of unhappy clients along the way, right? But it's all about that human interface to the machines that is going to be improving over time.
All right.
Thank you for your question.
If you don't mind, I just want to ride off of that question and can sort of take it in the opposite direction. We talk about the limitations that machines are placing upon our interaction with them. I'm just wondering if you can see any limitations on the other side where technology will outstrip our ability to deal with it. Like my grandmother, whose VCR still flashes 12 o'clock, there are times when we just give up and throw up our hands. Do you think that technology is going to advance faster than we can adapt to the changes in technology?
It's a good question, and Luke might be able to answer this better because he specializes in history, but I think that I don't think it will, because it can only advance as much as we make it advance, right? Like there's always going to be people who understand it and who are capable of moving it along, right? Like the technology cannot advance if we can't envision how it's going to advance, because we're making it happen. So that's just my thought.
I mean, I agree with that. I think that one of the things that we have seen maybe too little of in the last 50 years, certainly 25 years, right, is the integration of science and technology policy advisement into government, right? So, there are lots of folks around the world who understand how AI works, who understand how robotics work, who can talk about the pros and cons of specific different systems, et cetera, right? And I don't think those folks get listened to as much as they should be. I know we have a chief scientist in the Prime Minister's office. I think that's great. I think we need more of that, right? Technology, the word technology itself has a history, and we tend to kind of see it as this unstoppable force. These days we think of AI as an unstoppable force, but you can insert whichever technology you want. But these are tools that we create, right? And absent that artificial general intelligence, which again, once again, will not come in the next 50 years. Humans will be the ones who ultimately have the say over this system. Now, which humans, like who's making those decisions? That's a big question, right? And I think I'd like to see all of us be more engaged in those community decisions, and not just a few people.
My question is about climate change and affordability when it comes to adaptation or mitigation. You talked about the 100% renewable. I know that's being pushed, but affordability currently, we're struggling as is, keeping up with current technology. What do you envision would be like a realistic goal for the ordinary citizens? And
Thank you so much for that question. It's a really great one. One of the things that I work on is building decarbonization for our homes. So the way that we change our homes so that they can be part of a sustainable energy system, so they're more efficient, so they have some of these technologies like renewable energy or heat pumps. And the focus of our research is trying to understand how to accomplish these transformations of our homes for the homes that need it the most, the ones who are already struggling with affordability challenges. And so I think the key answer to your question is that we can't roll out all of these solutions for our energy system as market solutions for the affluent, as the same as a marble countertop, an upgrade for your home that improves the home value. It just won't reach everyone if the only kinds of policy tools or implementation strategies or investment strategies that we use focus on the market mechanisms that make it so that only people who can afford to pay for it out of pocket have access to, whether it's renewable energy, whether it's a heat pump, whether it's home efficiency. And so one of the things I think about a lot is the ways that we can recognize how much public good is coming from the transformation to our homes and invest in that change to our homes with public investment as well. And so the other part I want to answer for your question was there's been a real focus on individual solutions, like a consumer choice. And that's part of the climate delay and denial strategy, to redirect us away from thinking about systemic change, collective change, making it so that the default choice is a more efficient home, and making it seem as though it's an individual guilt solution as well. It slows us down, it keeps us entrenched in fossil fuels, and so I think the way forward is both to think about how we make it affordable for everyone using not just the market mechanisms we've been using, but also resisting the frame that's been put around climate action saying this is all about consumer choice, and instead thinking about collective systemic change.
Hello, I'm not sure who my question's for, so you can figure that part out. I'm a public school teacher, and I see the heaviness of mental health on young people. And if I imagine a flourishing future where we do flourish, I wonder what your thoughts are on how we educate, but also how we raise our children.
I can try to start with this too, because I did some work last year with a bunch of young people in Toronto and heard a lot about this challenge and heard a lot about how they want more climate change in their schools and in their homes. And the thing that I tell young people whenever I talk to a group of them is, first of all, to validate that this is a scary existential crisis. They don't hear that enough. They feel brushed off from the adults in their life. But also to focus on the fact that we can solve it. A lot of them said, no one's ever told me we can solve it before. And the last thing I tell them is that if we know from research that people feel better when they're experiencing climate distress, we know that people feel better when they find a way to take action in community. Any kind of collective, a group, others to work with. So I encourage people to find that group for themselves, neighbors or on a topic or in your family, any group. It's that collective doing something in the context of knowing that everything that we do matters that I think helps young people a lot.
And you can have your students listen to Quirks and Quarks because we've had a lot of optimism here tonight. Well, I just got a signal from the original producer of Quirks and Quarks to wrap it up. So, Diana, you're still active. You're still active. You're still with us. Well, that's it for our 50th anniversary episode of Quirks and Quarks. Thanks to our amazing guests. Thanks to the incredible staff. Thanks to the incredible staff here at the Perimeter Institute for Theoretical Physics for welcoming us so warmly, and thanks to you, our audience, for sticking with us for 50 years. Quirks and Quarks is produced by Rosie Fernandez, Amanda Buckowitz, and Sonia Biting. Our senior producer is Jim Levins. I'm Bob McDonald. Thanks for listening, and we'll see you next week. Thank you, everyone. Good night.